Igual no el té. Sí, sí, sí. Va.
Okay, good afternoon and welcome back to the sessions. So as you know, by the program, we are having now 3 talks in a row before the next business-to-business meeting, and then at 7 we will have a welcome reception in the floor below. So to start with this afternoon, we have a talk by Carlos Oriach, Monocrom, which is one of the main sponsors of the event, and the title is Lasers for Raman Spectroscopy in Mars Exploration. So welcome, Carlos.
Thank you very much for the introduction and for the opportunity of being here. So the very first thing I would like to say is that although I'm the one presenting this project here, or the results of this project, or work in this project, I have not been the person doing it personally. So first thing I would like to do is to acknowledge my colleagues, Marta Gilaberte, Paul Ribas, Sergi Ferrando, and Denis Guillot, who are the ones who, among these 10 years of development, have been really in deep working on this project. So the very first thing, sorry for a bit of messing with the fonts, but I work with OpenOffice, and apparently Microsoft doesn't like it, so he changes whatever I've done. I'll present briefly the company. We are a laser manufacturer based in Vilanova i la Geltrú, which is 40 kilometers south from Barcelona. We are a team of 50 people right now there after 25 years of working. And we basically do these 4-5 business lines that you can see here. We work in the low power diode lasers, the high power diode lasers, so basically stacking laser diode bars, which is our core business, and I will briefly present the key technology that we have there. Diode pumped solid state lasers, like a natural extension of the HPDL division. Right now we are developing these subsystems, which are mainly really high energy solid state lasers. So we have done in the lab some Joule class lasers. Okay? And laser electronics, like a kind of side business that we always had, because we had to develop our own drivers, controllers, etc. So we can still make electronics for the market, although it's normally internal consumption. So as I was saying, our core technology is on the high-powered diode lasers, and it's basically a different way of mounting laser diode bars. So this is a classic technology to mount laser diode bars. You can see, let me check if I'm doing it right. You normally have a laser bar, which is something as tiny as 10 millimeters per 1 millimeter, 10 by 4 in the biggest case, that is normally soldered via an indium foil on a copper heatsink. You place an isolator, of course, to prevent shortcuts between the anode and the cathode, and then you do wire bonding normally between the cathode and the laser bar. Though this technology is nowadays a bit outdated because it has certain drawbacks. The indium is quite soft. It can break during post-operation modes. You have some thermal cycles there that end up being mechanical stress on the laser bar because of the mismatch in the coefficient of thermal expansion of the different materials. So the industry has gone to something like this thing here, where they mix the different materials in order to try to match the CTEs and avoid this mechanical stress that you have between the different elements. What we made at Monocrom, like I think it was 14 years ago, 15 years ago, was to do something as simple as imagine a way to avoid the weak part. So the weak part was normally the indium soldering that has been, let's say, substituted by different kinds of soldering and different materials, paying a price in terms of heat dissipation. So what we made is something as simple as avoid any kind of soldering in our mounts. So we basically do a sandwich between electrodes and laser bars, giving us nice advantages when compared to the soldered technologies. When it's, sorry, this one is not moving, this should disappear from here, so allowing you to read this. But basically means that we can mount everything at room temperature instead of heating up the samples at some hundreds degrees, so 250 typically. This means that as we do everything at room temperature, when it cools down to operating temperatures, the laser bar, the diode, is not being bended. So we avoid what is the so-called smile effect, which is a bit disturbing when you need to play with micro-optics afterwards. We avoid the problems having CT mismatches because basically you work in cycles of 20 to 60 degrees at most. So at this, with these temperature ranges, you don't have huge problems. There is no soldering. The bar can expand and contract differently to the copper, and that's it. And in fact, we also have like a side advantage, is that we avoid, as we need to clamp, we need to press, we can avoid the wire bonding, and we have copper in direct contact with the laser bar from both sides, the anode and the cathode. So we have twice the thermal dissipation that the normal mounting techniques have. So we can use this better performance to deliver higher energy per pulse, or maybe to deliver exactly the same, avoiding the microchannel cooling that has also some issues for the industry. So I'm presenting this because it's the key technology of the company, but also to stress something that regarding this project, it's a bit unique. So we are a company that we are known because we are solderless when we do these stacks. And on the other hand, on this project, we had to do a soldered solid-state laser, which is also a pretty much different approach and is something quite unique for us. So the project I'm going to present, or our work in the project that I'm going to present, is something that has been done in the framework of a collaborative project in whole Europe, you know, the ExoMars mission. The orbiter has already been launched. The rover, where our instrument should be, is scheduled for the 2020, sorry, for the launching window in 2020. This is a project that is, the leadership belongs to the INTA, the National Institute of Space Science. Here we are LIDEX and Monocrom as subcontractors for different parts, and the IOF in Jena in Germany, which is also being part of our work packages to do these soldered resonators. So the very first thing that I want to stress is that the initial requirements for a laser that is going to travel to Mars are nothing unique in terms of a laser. If, sorry, the lines are missing, but if you have a look at this laser model is intended to do Raman spectroscopy. Just really briefly, for those of you who are not familiar with, it's basically exciting whatever component and taking advantages of the, let's say, relaxation. So you normally do not have all the particles or the molecules of a sample at the fundamental state. They are normally at some of them are at higher energy vibrational states. So you can excite these things, and a small part of the scattered light will have an inelastic scattering. So this means that the shift, they will have a little shift in wavelength with respect to the excitation wavelength that you have. So the very interesting thing or very important thing of a laser intended for Raman is basically the line width, because you want to be able to distinguish between, let's say, the elastic scattering that will have exactly the same wavelength of the excitation, so the same wavelength of your laser. You want to distinguish between the Raman and anti-Raman de-excitation paths. So you need a very, very thin line width. The one we have achieved is much smaller than this. For the rest, of course, stability, etc., but all these parameters are not that strange. You can find commercial lasers delivering exactly this. So the key point of this laser is that you want to launch it to Mars. And what does it mean, though? So it basically means that it will suffer super strong vibrations during launching and super heavy, let's say, shocks when landing, because landing on somewhere where you do not have atmosphere will mean severe impacts. But not only that, if you go to Business Insider, Tech Insider, you will see that in order to launch 1 kilogram of charge to low orbit, so to the International Space Station, will cost like $20,000 each kilogram. If you want to go to geostationary orbit, it will be twice that. If you want to go to outer space, it's more than 3 times the second quantity, so 6 times the 20. Let's put 100,000 euros per kilo. So the weight is really important in this kind of devices. Here we have a super strict requirement also in terms of weight, 100 grams roughly for the module plus all the enclosure, all the housing. Also the size is important because you know that volume means weight. So what did we do in this project? It's basically what Dr. Munoz showed in the first presentation today. I think it was the third or fourth slide. So we're starting from something that you can have on the lab, really big. This is the laser. So it's most probably like 10 centimeters. This is a laser that can do the work. Green laser, small line width, a bit of electronics around, and that's it. But it was the first demonstration. Yes, the laser do exist. We can do that laser. What happened afterwards was, well, here I'm just showing that the laser here is the solid state laser. It's just the resonator. Here you have a pumping diode. So you need to increase this size a little bit. Laser pumping diode. The first evolution, trying to squeeze a little bit the things, was putting, again, pumping diode in here and a much smaller resonator. So first step was trying to miniaturize the resonator. It's much smaller, but not enough. So the very first real demonstrator of the laser has been something like this, small, pumping diode again. This was the resonator. This is roughly the size of a 2 euros coin. It was the very first thing that we presented, although the diode was still external. So here you just see, well, this is the diode coupling, this is the output fiber, and just a couple of photodiodes. This has one channel. And this was quite successful, so this was the first unit that went to space qualification. Okay. It had some results that were okay. So for Raman, the exact excitation wavelength is not crucial. So we had, as you can see, a huge tolerance here, 532 plus minus 4. Although, as you can see, the bandwidth, the line width requirement that was 30 picometer was not matched. This is just a couple of, let's say, three cycles of measurement wavelength. No, nothing unique. The evolution of the central wavelength is also critical. You cannot change the wavelength during an experiment that will take some minutes. So basically you can see that the peak wavelength was jumping roughly half a millimeter, so still one order of magnitude above the initial requirement, unfortunately. And also regarding the stabilization, which is pretty much important, as I said, during the whole experiment, we saw that we had like a strange, this is in terms of power versus time, strange behaviors in the laser output that was for sure not matching the stability needed in the requirements, but the good news here was that there is a plateau, and we managed to see that the plateau is basically correlating quite well, pretty well, with the pumping current and the temperature of the laser diode. So from here, we understood that there was a lot of room for improvement, but we had to change a little bit the design. We also see that when you send something to space, the last thing you want to happen is it to break, but if it breaks, you need to have redundancy. So we need to have two beams, two lasers in there, and couple them to the same fiber and so on. So the simplest way is to have a polarization beam combination. So we needed to have a really high degree of polarization, which was not matched neither in the first tests. So this is what we learned during the first 4 years of the project, first 4 years of development, till we reached the third prototype, which was basically what we tested in ground before launching to space. So what did we do in order to make a laser that is capable of withstanding all that requirements, mechanically or environmentally, while at the same time delivering the beam performance or the wavelength performance that we needed? So we basically had to change a little bit the setup. The first thing is that in order to stabilize correctly the laser diode, we needed to integrate also the laser diode inside the package. So instead of having a beam entrance, here you see that we have directly two diodes soldered, in this case, inside this third prototype. This helped quite a lot to stabilize everything. Then we had to change the active material. We were working with a vanadate because it had a wider absorption spectrum, which is beneficial in order to be able to play a bit more, to enlarge the temperature range of the diodes. But as it was quite impossible to work with that, we had to change to a classical NG-YAC nonlinear crystal in here. We also changed, of course, the output coupler to something with a slight curve in order to correct a little bit the thermal lens. And we added the redundancy channel. But still, we glued all the components. Why gluing? Mechanical fixing is just impossible if you want to achieve this size. So this 2 euro coin, let's say, is just impossible to have if you have to use screws. There is no way. On the contrary, you have some glues that are really low in outgazing, like these two referred here. But what it came out of the trials is that, okay, we matched all the parameters with this thing. But unfortunately, this was not stable enough a long time. So the glue seems to keep curing over some weeks, months. So there were small misalignments in components that completely make the laser completely unusable. And here is where we decided that although we are a solderless company, we had to go to soldering the components, but not soldering them in a normal way. So you can see here, this is the soldered resonator. There are only two components soldered in, let's say, standard methods, which is basically the diodes. They have a soldering foil. You just heat it up. It melts and it fixes. And the YAC in here, which is basically solved by flip chip techniques. All the rest is where the Fraunhofer Institute enters. You can see small droplets here shining, also a couple in here, which is using something quite new, quite unique. This is called solder jet bumping technique. Okay? So this was basically the resonator with two outputs, one going here and one going here, with the soldered components, the very first one we made. And, well, as a basis of comparison, you have a nice needle. And finally, because of this, we just changed it, as you can see, the active material, medium. We split it in two. It makes the process a bit more complicated, but you can achieve better alignments. So now we can just have a look a little bit more on what kind of resonator do we have here. We have one in here, second one in here, just showing here the diode, which is basically a 1 watt optical power diode with it's an diffused feedback, distributed feedback diode. So it's pretty good in terms of wavelength stabilization. Here we have a fast and slow axis collimator to collimate the beam. You know, from a laser diode, the beam is quite divergent. The ND-YAC, a BBO crystal, so we are doubling the frequency from 1064 to 532 intracavity, an output coupler, just a bending mirror. And here you have essentially the same, but we add a half wave plate in order to just change the polarization. Before going to the PBS, the polarization beam splitting cube, and then everything is redirected here where we are just now lacking the focusing optics, and here we would have the fiber afterwards, so a 50 micron fiber. This is pretty small. You can see that we had a target of 111 grams for the full module plus housing. Well, the module itself is just barely 3 grams here. It's pretty small, pretty lightweight. How did we come to this conclusion? So it's basically how did we choose all these materials? So surprisingly, we have two different criteria. There are two materials that are quite inefficient in terms of optoelectronic efficiency, which are basically the diode, 50% roughly, and the ND-YACs, 35–40% at most efficiency. So these two guys here, this one and this one, also of course the redundant ones, need to have a super good thermal dissipation, because this will be enclosed somewhere. So here we basically choose as a base plate bare copper. Copper has a super high thermal conductivity. It's pretty good to dissipate the heat that these two guys here will generate. But these are the only two. All the rest are chosen because of the CTE. You remember in one of the first slides, I was talking about the problems in CTE mismatch. And this is also a problem for this laser. Although the heat that is going to be generated, especially in the BBOs, is not that much, you still need to have something super stable. Remember that it will travel from ground Earth to ground Mars with all the travel in between that it means, so the thermal cycles could create some misalignment. So the very first thing is to try to choose components which CTE is essentially the same, especially in the resonator part. So you see that the base plate is aluminum nitride, the pads, which are these bases here, or this here, which is seen a bit more clear, it's based off copper. The second harmonic generator, we chose BBO exactly because of this reason. No LBOs, no KTPs because of the CTE. While the substrate of the optics, so the output coupler and this polarization beam splitter cube and the bending mirrors is fused silica. This is quite low, but it is what it is. It's standard components. The soldering material we are using, which is basically a mixture of indium, tin, and something else. Heat sinks, well, at least you can see more or less here the different materials. The main idea is that all the resonator has to match the CTE as much as possible. So finally, this is a completely finished setup. This is the housing I was referring to all my way around with a fiber optic connector, 2 photodiodes, one to monitor the power of the laser here. So with the bit of light that this bending mirror will allow to pass through, we can close the loop via PID with the electronic input in the 2 diodes, or in 1 diode, because they are not working at a time, so it's just one or the other working. And here we have a small pinhole to ensure that we have a nice single mode beam. It's filtering all the rest of the beams, and with the bit of light that is coming back, it can monitor, it's a feedback for the autofocus that is being done by Inten, you will see later on. So this guy is the one that is going to Mars, in fact. We already finished the flying models campaign, so out of 5 that we made, 2 are ready to go to Mars. But before that, of course, there was another model that we made with only 1 channel. You will see later on the results, which is the EQM, and we will be able to compare the results we had before with the results we have right now when moving to solder jet bumping. Solder jet bumping is something that I would like to explain a bit more, because it's, to my knowledge, it was quite a unique thing. It is developed by the Fraunhofer IOF in Jena, as I told you. So, and it's basically consisting of filling kind of deposit with a small bumps, small balls of whatever soldering material. In this case, this SAC3, not this one, the one I mentioned before, 305, SAC305 here. You have a nice disc that is basically matching the size, but a bit smaller, the size of the ball that is delivering each ball to this chamber here. And in this chamber, you have an IR laser together with a nitrogen flow. So the IR laser will just melt the ball sufficiently to pass through the small hole that we had here, not more than that, but sufficiently to melt let's say, the outer region of that ball, and the nitrogen flow will just throw it to the component. So this way we can control exactly the size of the bumps, the size of the soldering balls that we have there, and at the same time, when it reaches the component, the amount of heat you will have, the energy you will have, it's super low because of the small size of the ball. So there is absolutely no movement in the component during the soldering project. This was really, really important because the precisions you need in mounting this resonator are really demanding. So this is just a scheme of this solder jet machine that they have in the IOF. And here there is just a real picture, so you can match the sizes of everything. This guy here is just a 6-axis positioner, so we need to control X, Y, Z, and tip tilt. This is how this guy is done. And finally, let's say this laser here with just one channel was what was sent to the qualification campaign before going to Mars. So when we achieved, in fact, all the parameters and exceeded, in fact, all the parameters in terms of shocks and vibrations, you can see it's pretty hard. You have nice shocks here. The operational temperature range, which is non-operational, sorry, is quite large, so it's in order to prevent any movement during the travel, although the operational temperature range, which is wider than the requirements, is not huge. So it means that all the setup will need to be thermalized while in Mars. It also passed the proton radiation, quite demanding also proton radiation, and the gamma radiation. These two requirements here were also a bit tricky for certain glues that we tried at the very beginning, but luckily all the soldering technique is completely insensitive to the proton radiation and gamma radiations. So this is basically what the laser has been able to do. And here the final results. As you saw at the very beginning, the wavelength was not super critical, but the line width it was. We needed 30 picometers. We went to 10 picometers. So we increased with this, thanks to the stability of the resonator, we increased the resolution of the system. This was one of the key points. The stability, as you saw, by thermalizing, it's already overcome. And this is what I can show you as part of the scientific contribution. So this is really protected. You know, the first results will be published by INTA pretty soon, so I cannot put the preliminary results that we have in here, but we have the laser which is embedded in some part in this electronics box. Here you see an autofocusing head, just basically optics with a fiber in and a fiber out. You see the green laser of our laser here, and this is the spectrometer. So this is the setup that has been tested successfully with very nice results, being able to distinguish clearly between old Martian souls, new or recent Martian souls that have been reproduced artificially at INTA premises. Hopefully pretty soon we'll see some results published, most probably in astrobiology or different conferences. So unfortunately I cannot show them here. But if you want to have some further information about the laser or about the full instrument with the scientific part behind, you can recall to these publications here. Of course, if you need anything further, I'll be happy to answer here or over email. I don't know if we have time for questions, but I would do a small different thing. You normally wait for the audience to ask to the person talking, and I have a question for the audience, the other way around. Would a laser like this could be done with peaks? Like we have something that is tiny, but what about the nonlinear materials that we have in here? Can you put nonlinear materials in a peak?
Okay, let's thank. So now there's time for questions. So the first question was done by Carlos. Nice. So who is willing to try to answer that question? The materials guy, yeah, there are the materials guy on the back side. So I think that maybe Juan is going to kill me. Hola, Juan. There is Carles from Monocrom. They did a DFV laser at 1000, and they use it's neodymium YAG, right? Non-linear material.
Yeah, the first non-linear material is
and
neodymium
he's
YAG.
Asking if we can put such a kind of material in a photonic integrated chip.
I think it's difficult. Because it's difficult to integrate a laser. It's external, is quite big, and the material is What is the material?
Neodymium yak for the first nonlinear crystal, BBO for the frequency converter.
Yeah. No, that's
But it would be nice because every laser we have to do, we need to go to Jena to do the solder jet bumping, so it's quite costly.
Yeah, yeah. Well, it seems to be difficult. So you actually made a trick question to the audience. Well, but I do have a question myself, if
sure.
you allow me. It is. Can you tell a little bit more about the resonator? I don't think I didn't get.
It is a pretty simple one, in fact. So it has absolutely no secret. It's a linear resonator. So first thing you have is the laser diode here. You can see the gold wires in here. So then we have fast slow axis collimators. They are not clearly seen here. Maybe we can go to the scheme, which is a bit better in this sense. This lens here, the first side is collimating the fast axis. The second side is collimating the slow axis of this diode laser. Then this part here is the neodymium yak crystal, so converting from 808 to 1064. This other material is also nonlinear. This is a second harmonic generator, a BBO, so it's taking the 1064, converting to 532. And this is the output mirror, the output coupler. I do not recall by memory the curvature. This is a curved mirror in order to compensate the thermal lens, especially of the ND yak, which is the one that has a higher thermal lens. So this is essentially the resonator. And this is exactly the same because it is redundant. The only difference is that in this second path, in the redundant path, we have a half wave plate. So the light from here, from an ND yak, is strongly polarized, vertically in this case. This is basically rotating from S to P, the polarization. So by means of this beam splitter, we are able to put both polarizations, so both beams, in the same optical path exactly, although they are not working at the same time. So it's redundant, so if one fails, the other one will run. But you need to ensure that both of them have the same performance on the sample, because up there in Mars, you will not be able to change the settings. So everything needs to be done in Earth. So here, we are only lacking, this is a pinhole. These are just two bending mirrors, 45 degrees, and that's it. And here we are lacking 1, 2, and 3 components that are basically taking the collimated green light and focusing it to a 50 micron fiber, 0.12, I think, numerical aperture, which is the one delivering the light to the sample itself. So it's, as a resonator, it's fairly easy to do. I mean, it's a linear one, no tricks in here. The only wavelength stabilization techniques used here are thermal control and the diode itself, which is a DFB one.
So there are like two wavelength conversion stages,
yes, right.
Okay.
The first conversion stage here, 808 to 1064, and the second one here, 1064 to 532.
Okay, thank you. That's clear to me. Any question?
Just to clear my mind, so when you say resonator, is the frequency downing?
No, for No, the resonator is because this material here, apart of being ND yak, I haven't said so, but this side here has a coating, and this coating is allowing 808 of course, to pass through, to reach the crystal, but it's blocking, it's reflecting everything in 532 or 1064. So basically light keeps between this element and this element resonating, and just a small part of it is just allowed to go out of this resonator. 15%, I think, it's allowed to go through the output coupler. So resonator is basically this. If we were not using an internal BBO, an intracavity BBO, I would still call it the resonator, as we have light resonating between this mirror here and this coating here, which is acting as a 100% mirror for the 1064 and 532 light.
Okay, now it's even more clear to me. Thank you, David, for insisting. Any other question? No? Okay, so thanks, Carles.